Hello, everyone. My name is Aaron Fox, and as a part of our computer architecture course for the fall of 2020, I'd like to give you my research paper presentation on the paper titled Reconsidering Complex Branch Predictors. To first give you some background on the author of this paper is Daniel A Jiménez, and he wrote this during his time at Rutgers. He maintains quite the expertise in branch predictors. He is one of the leading figureheads in the field of branch predictors and improving microarchitectures in general. He has dedicated all of his time during his professorships at the University of Texas, San Antonio, University of Texas, Austin, and at Rutgers, all mostly dedicated to branch predictors, the different algorithms involved with them. He's worked on seminal papers about piecewise linear branch predictions, neural branch predictors, and basically has a hand on any modern predictor systems that's being researched right now, either as an influence or as a direct author of those papers. And if you are ever in doubt of this gentleman's authority in the field of branch prediction, let it be known that on his own website, he maintains a section for branch prediction jokes, which is a rather niche field of comedy if I've ever seen it. To provide a little bit of context about when this was written and why, Reconsidering Complex Branch Predictors was written back in 2003. Microarchitectures are getting larger with higher throughput rates, with often deeper pipelines. They're having more aggressive clock rates. And the designers of these microarchitectures are throwing a lot of transistors on these chips, which these branch predictors can use. And so on the right here, you can see is a picture of the DEC Alpha AXP 21064 microprocessor die. This microprocessor was designed in the mid-1990s, and microarchitects are basically building on top of this with more complex and more advanced microprocessor versions such as EV5 and EV6 with larger secondary caches on chips and higher operating frequencies combined with out-of-order execution all built in. So they're throwing a ton of transistors on these dies, they're building on top of them, and microarchitects are getting very excited. The zeitgeist of this time was basically more complex and more aggressive clocking, and so microarchitects followed this by building larger and more complex branch predictors. And so Jimenez noted this obvious trend that branch predictors are also getting larger and more complex along with the microprocessor. So it's corresponding with this large booming growth in microarchitectures. And so as a result, these branch predictors are also getting more and more accurate. You can see also the hardware budget of these branch predictors is also skyrocketing. It's getting much larger. Of course, back then, to contextualize it, skyrocketing means hundreds of kilobytes of growth. Now it's even larger, and that might seem like small dice to us. But back then, it was huge, and it was a big change. And on the right here, you can see is a compact alpha 21264C microprocessor, which itself included a hybrid branch predictor with approximately 45 kilobytes of state, which was a huge increase in size at that time. It's a big achievement. It's a lot of data for a lot of capacity for just a branch predictor at the time. And this figure kind of shows what I just talked about. It shows the arithmetic mean misprediction rates achieved over the SPEC 2000 integer benchmarks using several branch predictors that were famous in literature at the time. It extends these predictors into large hardware budgets, which is the focus of this paper. And you can see the higher accuracy that's shown by the more complex branch predictors, such as the multi-component hybrid and the perceptron systems. It looks very appealing, but as the main point of this paper argues, better accuracy doesn't always mean better performance. And that is basically the essence of this entire paper. If I could sum up this entire paper in one slide, this would be the slide I would give you. And so unfortunately, a large hardware budget and complex organization doesn't directly correlate with performance. In fact, with even larger, more complex branch predictors, the increased complexity often leads to branch predictor delay, which has a negative impact on performance when compared to equally large but simpler branch predictor systems. This is a result of the branch predictor being on the critical path for instruction fetching. The branch prediction really needs to be retrieved in a single cycle. However, the deeper pipelines and aggressive clock rates that are found in modern architectures often increases the access delay, and this requires complex techniques that involve costly performance penalties that we'll get into. And this figure here shows the instructions per cycle of the complex perception and multi-component predictors. You can see there's one is realistic, one is overriding, and in an ideal world, the performance of these branch predictors are fantastic, and they effectively increase as the hardware budget increases, which would be wonderful. You can give it more power if you give it more hardware, which is what you'd expect. However, the practical implementations with realistic access delay illustrates how the performance actually drops off as the budget increases, and that's a big problem. At the time of this paper in 2003, this was really hindering microarchitects' abilities to build larger branch predictors, which limited their budget to smaller amounts of kilobytes, which really restricts them because they have the capacity now to throw on a lot more transistors. They should be able to take advantage of this advanced hardware budget that they now have. They have more money to spend effectively, but they can't spend it. And this really illustrates the necessity of another predictor organization that can hide this punitive access delay other than what we had right now, which is what Jiménez is looking for in this paper. So to give a little more context, here are some examples of complex implemented branch predictors in actual real-life microprocessors. So to give a little context on why the implementation built up in this paper is important, these are some examples of some rather complex versions that use these rather complex versions of branch predictors. On the left here is the Alpha EV6 core that uses a hybrid branch predictor that is composed of two-level predictors. It uses a 4 kilobyte entry pattern history table that is indexed by a global history register. And it also uses a 1 kilobyte entry pattern history table indexed by one of 1024 local 10-bit branch histories. The final branch prediction is then chosen by indexing a third pattern history table. If this implementation sounds a little complex, that's because it is. This complex implementation is very costly. Whenever the more accurate branch predictor disagrees with the less accurate line predictor, a costly penalty is then incurred every time. And on the right here is a second example with AMD's Hammer architecture, specifically the K8. This uses a complex branch predictor scheme of an array of branch selectors that decide whether to use two-level prediction for difficult predictions or to use simple branch bias predictions for easier predictions. This uses either a whopping 16 kilobyte entry pattern history table index by a global history register, or just a more simple prediction for bias branches. So this also incurs a penalty as a result of the complexity of the branch predictor, since selecting which branch predictor to even select to begin predicting is itself a performance hindering process. This is also very complex because it has to even do several computations to even decide which predictor to use, and that is kind of like predicting which predictor that should be used, and that's just so much complexity that you can kind of begin to visualize how this is hindering the performance and the IPC of microprocessors at the time, even with hardware budgets. Moving on. Moving on to some of the causes of complexity in these branch predictors. So complexity in branch predictors ultimately arises from using too many levels of logic on the critical path to making a prediction. Some examples of this are using large tables that are indexed by the branch program counter. If a branch predictor has to fetch a target address from a large table, the high access delay will incur a penalty, just like with large caches. And also with complex computation, kind of like I just talked about the hammer architecture. If with hybrid predictors, they must combine data from different tables to compute a final prediction. This delay in computing can stem from complex functions inside the branch predictors and often leads to delay because there's more computations within the actual predictor rather than just a simple like single cycle going straight for the prediction. And also, unnecessary dependencies also are a bad cause of complexity. If the branch predictor relies on the branch instruction contents too much, the instruction cache is put on the critical path to making a prediction, which itself causes more opportunities for delay due to the inherent complexity of the dependencies. And so many branch prediction schemes try to get around these complexities with delay hiding techniques, just like overriding. But the penalties incurred over time are nonetheless very noticeable, and they put a damper on performance. So let's take a look at the impact of delay and how we could possibly mitigate it. In a previous paper by Jiménez, he shows how even a 100% accurate predictor with a latency of 2 cycles results in worse performance than a relatively inaccurate predictor with single cycle latency. And this illustrates that even with more accurate and therefore more complex prediction algorithms, they can counterintuitively cause worse overall performance. And there are some popular techniques for overriding the delay inherent to these more complex and more accurate branch predictors, or mitigating the delay. Um, one of which is overriding predictors. So overriding predictors take advantage of 2 different branch predictors. There is a fast but inaccurate predictor, and there's also a slower but more accurate predictor. So you can kind of think of this technique like the train tracks a metaphor. Let's say there's a fast, inaccurate branch predictor, which effectively builds out train tracks for the train to follow. But if the fast prediction is disputed by the slower, more accurate predictor that's slowly laying out those tracks, the processor, that is the train, has to backtrack the train all the way back while the train is already halfway through the fast tracks, and then rebuild the tracks based on the more accurate prediction. So you can see why that's slow. Because the train has to go all the way back and then forward. It was already down a path, and then it wasn't right, and it was disputed. So there's a lot of lost time there. So the costly penalties of this technique are pretty apparent. Although this technique can save some time whenever the faster predictor is correct, which is why it is used and implemented in some microarchitectures, and it was very popular during the time of this paper. There is also dual path fetch, which is used in the AMD Hammer architecture that we discussed a couple slides ago. And this takes advantage of extra cycles that may be available after an instruction cache line is fetched from a previous branch prediction, and then it starts executing instructions on the branch that is not predicted, just in case the initial prediction is incorrect. So this allows for speculatively executing down both possible branch paths, which is pretty creative. However, this technique basically halves the instruction fetch bandwidth, and this exhausts all the available resources, which adds to the complexity penalty that we discussed earlier. And it's very creative. It goes down both paths. It's basically like saying, oh, it'll definitely go down both or one or the other. But by that, they're using all the resources, which adds a lot of complexity, which lowers the overall performance in IPC. So let's see, Jimenez is to the rescue here. So having discussed some of the troubles inherent to complex and large, highly accurate branch predictors at the time of this paper, Jimenez proposed a simple, large branch predictor. His predictor can be pipelined to deliver every prediction in a single cycle, which solves the issue of access delay. And their solution applied this special pipelining technique to a previous version of the classic G-share branch predictor. G-share, or global sharing, is so called because it combines global history with branch addressing to better index and identify a table of prediction bits for future predictions of branches to take. So he's building on a classic version of a branch predictor system that was already out in the literature, and he's building on that, but he's adding this special pipelining, which is what makes it able to be scalable as the hardware budget increases. So let's dive into the basic idea of gshare.fast, as he calls it. The main idea for allowing pipelining of the branch prediction in a single cycle concerns the organization of the branch predictor. It maintains a small set of candidate entries in a pattern history table, which is prefetched several cycles before the prediction is even needed. And this figure here on the right shows the concept of how the entries are whittled down and selected for the final prediction. As more instructions are executed, the location of which entry is needed becomes more and more clear. Eventually, when the branch prediction is needed, the prediction will be ready after it goes through the large pattern history table to the buffer to the prediction. It's all going to be ready when it's needed. And additionally, this predictor avoids using local histories, computing complex hashing functions, and creating dependencies between the branch address and prefetched pattern history table entries. This greatly improves performance over more complex predictors, which often fail to avoid these more costly techniques. So what are some of the perks of gshare.fast? To summarize some of these perks of this fast gshare implementation before we go into the details of the nitty-gritty details of the implementation, here are some of these perks. It is highly accurate, which is still an important factor for any predicting system. It also takes advantage of a large hardware budget, which is more and more important as microarchitects are able to, as we say, throw a lot more transistors onto these chips as technology advances. And as mentioned previously, it is able to take advantage of pipelining to produce a prediction in a single cycle. And this is necessary for avoiding prediction delays. And it also uses the most updated history, which is very important for providing accurate predictions that avoid using obsolete data. You can't just make a fast predictor system, but it's not accurate. That wouldn't be productive. So it also uses the most updated history, which is very essential for an accurate system. And as a result of these, no extra penalties or complexities are incurred for the rest of the pipeline, which saves a lot of time for the processor. And lastly, the predictor reduces design complexity by minimizing interaction with the rest of the microarchitecture. This is very important and easily seen when gshare.fast is contrasted with the alpha EV6 and EV8 cores that use the overriding technique, which, as we discussed before, with slow and quick predictors disagree. The instructions or fetches must be tossed out and restarted anew, which is very unproductive. And there, the microarchitecture has to keep track of two different types of speculative instructions. Those instructions that were predicted by the slow and those instructions that were predicted by the fast predictors. And even when they agree, the instructions predicted by the quick predictor have to be remarked by the microarchitecture. And this is a very costly interaction, which is avoided in gshare.fast because it avoids these dependencies on the rest of the microarchitecture. So let's begin to dive into the pipeline implementation, which is the core of what makes gshare.fast special. Because the pipeline runs in parallel with the fetch engine components, it only needs to interact with the rest of the components to receive a branch address, send a prediction, or recover from a misprediction. And this avoids unnecessary overriding or complexity overhead that is inherent to more complex branch predictors that were popular at the time. And the pipelining of this predictor has 4 stages. There are 3 stages dedicated to just reading the pattern history table. And each of these 3 stages keeps track of new speculative global history that have arrived since the pattern history table access began. And this always keeps the pattern history table up to date. And each stage of these 3 stages also maintains 4 latches. The first latch, the branch present latch, records whether a branch was fetched and predicted during the cycle. The second latch, the new history bit latch, records the speculative global history bit from the next pipeline stage. And the third and fourth latches both receive the bits from later pipeline stages, and these are used to assist record keeping. And the fourth stage is just one for computing the actual prediction, which is needed in all predictors. A final computation is always needed to decide which branch should be taken and which branch should be predicted. So this figure here illustrates the pipeline stages that are found in gshare.fast. In stage 1, on the very left here, the global history register is used to begin fetching 8 2-bit counters from the pattern history table into the 8-entry pattern history table found in stage 3. Also, the new history bit latch is shifted in from any predictions found in stage 2, and the branch present latch is then set. Otherwise, the 2 latches are just reset. And the multi-cycle pattern history table that you can see that starts at the large pattern history table and dives to the 8-entry pattern history table on stage 3. This multi-cycle pattern history table access continues in stage 2. The first half of the cycle sees any history and branch present bits forwarded in from stage 1. And the second half sees the shifting of those new history bits and branch present bits from stage 3, which always ensures an updated global history. By the end of stage 3, the 8-entry pattern history table is read from, and again, the new history and branch present latches are shifted in from stage 4, while its own bits are forwarded to stage 2. And lastly, stage 4 allows for exclusive ORing the address bits of the currently fetched branch with the bits of the global history register. The bits are then shifted and combined with the new history bits from stages 1 through 3, and this forms an index to the 512 entry pattern history table buffer. And finally, the resulting value is then used to select an entry for the predicted branch, which is then forwarded to the rest of the fetch engine for the engine to use. And that's the final stage. All right, so let's talk a little bit about how the predictor is updated. The speculative updates to global history registers are set when a branch is predicted on the assumption that the predictions are always correct, which aids in accuracy of overall predictions. This is accomplished through the shifting of the new history and branch present latches through the stages, which is why those were included in all 3 of those initial stages and forwarded in from stage 4 at the end. And non-speculative pattern history table updates are updated whenever a branch is executed. This pattern history table then either increments or decrements the prediction depending on if the branch was taken or not. So this pattern history table is slowly updated through the pipeline in gshare.fast, which has a very minor impact on accuracy versus a fast updating of the non-speculative pattern history table. But overall, the author noted that it was within like a few hundredths of a % of accuracy, and so decided that this was the slow updating of the non-speculative pattern history table was worth the speed up. And the misprediction recoveries occur whenever the branch predictor incorrectly predicts where the program should have branched to. And this requires overriding the speculative global history register with the non-speculative pattern history table, which is actually, since the non-speculative has the actual branches that were taken and not taken, that were decremented properly with what actually happened. So this does cause a latency, since this pattern history table will now be invalid for a few cycles. but they do help alleviate this delay by propagating up the pattern history table buffer toward the non-speculative pattern history table buffer, which is then used in the incorrect buffer's place. And so this relieves the delay of a couple cycles. Mispredictions happen in every system, and this is how Jiménez decided to take the misprediction recovery route with this, is shifting in and propagating the actual non-speculative pattern history table up towards to fill the speculative table to reduce the impact of the delay of a misprediction. That being said, there are some caveats to the implementation of gshare.fast that are discussed in this paper. Regarding multiple branch prediction, this paper only focuses on the simplified case where a fetch engine only needs one branch prediction per cycle. Modern microarchitectures, however, they often need many branches to be predicted at once. Jiménez notes, but does not elaborate too much upon how gshare.fast can be extended to provide many predictions in a single cycle by enlarging and extending the pattern history table buffer so that more than one branch could be predicted at once. Although this would lead to more complexity in design, Jiménez is able to describe in the paper how this would be very achievable in a single cycle still, with more entries in the pattern history table. Another caveat is that this implementation focuses on predicting whether a conditional branch is taken or not. It doesn't really concern itself with the branch target predictor, which requires a branch target buffer in order to know which address of the next instruction needs to be fetched after a branch. Therefore, a good branch target buffer implementation is also needed to be combined with gshare.fast in order to predict those actual addresses, which is very essential for an overall predicting system in a microprocessor. Regarding larger hardware budgets, at the time of this paper, the need for larger hardware budgets was not yet completely certain, although it did appear to be the clear trend at the time. Jiménez expresses confidence that his work will become more relevant as the hardware budgets increase over time with larger and larger on-chip caches. And with our current hindsight, we see that his prediction was very correct and that his work is quite relevant to today's world of caches. Moving on into the experimental results themselves. The results of testing gshare.fast are compared with the perceptron predictor and the multi-component hybrid predictor, which are the most accurate known branch predictors in the academic literature. And so they're very ripe for comparison with gshare.fast. And the previously mentioned EV8 cores branch predictor actually used this new, the shiny brand new predictor of this time. Kind of the context of the paper was the 2BCG skew predictor, and this was a recent and innovative predictor at the time. And each predictor results uses the overriding mechanism to prevent access delay, which is aiding in the fact that these are very complex and they're going to be probably more accurate, but as we will see, these are perfect for comparing with gshare.fast, which is a much more simple implementation, but also just as large of a hardware budget. So really the proof is in the pudding, because Jiménez uses very optimistic assumptions for these complex implementations, and he is able to really illustrate how fast gshare's implementation is actually far superior over the other implementations. So he makes these super optimistic assumptions about these complex implementations. So both local and global histories are updated speculatively and recovered with no latency after an incorrect prediction. This will give very good accuracy, but is actually very difficult to implement in reality, especially with larger tables. Hence why this experiment is biased actually towards these other complex implementations, which provides an upper bound on the performance achieved by these predictors. Another assumption is that for these other predictor implementations, the access latencies are optimistically assumed as well. For instance, the perceptron predictor only assumes a single cycle delay for computing the output. But in reality, these predictors would have much higher latencies in practical implementations due to the physical world, really hindering the latencies of these actual complex implementation. Additionally, another assumption is that the overriding penalty for the complex implementations are also assumed to be equal to the access latency above, which is also not practical in real life, but are optimistically assumed nonetheless to form an upper bound. And lastly, the clock rates of the complex implementations are also assumed to be a very high 3.5 gigahertz and 100 nanometer process technology. This assumption is, again, not really practical in real life implementations of these predictors, but Jimenez chose these over overly optimistic assumptions for the complex predictors to fully demonstrate the performance improvements of his fast G-share implementation over these other more complex implementations. Getting more into the actual parameters of the simulation experiments, Jimenez used the 12 Spec 2000 integer benchmarks to run a modified version of a simulation software called Simple Scalar Alpha, which is an accurate out-of-order execution simulator that was popular at the time. And this was used to evaluate these different branch predictors. And the first 500 million instructions are ignored in the simulation since those are often just initialization setup instructions, which aren't really relevant to the branching questions of this paper. And by the time the execution is finished, over 1 billion instructions are evaluated, which provides ample data for this experiment, I'd assume. Jimenez also notes the particular configurations used for each simulation. So since the same cache configurations, pipeline depths, branch target buffers, and so on and so forth are all set to the same input value for each branch predictor, the predictors are able to all start out on a level playing ground at the beginning of each respective simulation. Moving on to how the predictor access delay is estimated in the simulation. Each predictor has two delay components. One is the pattern history table access latency, and the other is the actual computation time needed for the prediction. The multi-component hybrid and the 2 BCG skew predictors were both assumed to have the latency of the largest table component, and it was optimistically assumed that only a single delay for the computation cost was incurred each time, which again is not going to happen in real life. The perceptron predictor, which has a more costly computation component as it computes the dot product of two vectors in the predictor, is also optimistically estimated to have 2 delay cycles, which would be incredible if that was real. And the pattern history table access times for this 100 nanometer process technology was all estimated using the Cacti 3.0 tool for simulating cache delay put out by Hewlett-Packard. And I've actually had the opportunity to play a little with this tool. It's now in its 7.0 version in 2020. And it's a very interesting tool for evaluating and looking at caches, whether it's the cache delay or other features of caches. And it's very useful, and it's cool to see that even back in 2003, this was a tool that was used by the leading figureheads at the time of branch prediction systems. This figure here shows the access delays that were computed, likely using the Cacti 3.0 tool for the multi-component hybrid 2 BCG skew and the perceptron predictors at several hardware budget ranges. But do note that these are the most optimistic assumptions for the complex predictor algorithms, and they will certainly have larger delays in realistic implementations. This figure here, it shows the misprediction rates of the 4 large predictors simulated over hardware budgets that you can see range from 16 kilobytes up to 512 kilobytes. You can see a pretty clear advantage and misprediction rates of the 3 more complex algorithms over the fast G-share implementation here. And this shows how more complex predictors, as expected, often do have better accuracy than simpler predictors. And the results of this experiment do confirm that assumption, especially at lower hardware budgets. You can see that the other more complex implementations far outpace the misprediction rate of fast G-share. So this is one of the most seminal figure of this entire paper right here. The figure shows the harmonic mean instructions per cycle, which is used to measure performance in this paper, that was produced by the cycle accurate simulations. The left graph shows the graph with the idealistic IPCs for each predictor. It shows how ideally in, say, a perfect high school physics problem, box on flat surface with no gravity world, the performance of the more complex predictors outperforms the fast G-share implementation for all hardware budgets. It doesn't deteriorate as the budgets increase. It's ideal, it's perfect, it's kind of how the math works out. However, the graph on the right shows what happens when the branch predictor latency of of more complex branching algorithms is actually taken into account. So you can see here the detrimental effects of overriding techniques that don't allow predictions to be given in a single cycle like the fast G-share implementation allows. Fast G-share, as a result, far outperforms the other complex predictor implementations as the hardware budget increases in the experiment. And you can probably extend that hardware budget to much larger today because it's been almost 2 decades since this paper was written. And so I think you can almost visualize how far those lines would extend out as those budgets were increased and how large that disparity of the simpler fast G-share implementation would grow over these complex implementations. So this stark difference between these two graphs can be explained by the fact that the overriding mechanism of the complex predictors relies on a relatively inaccurate first level branch predictor. So every time the two branch predictors of these implementations disagree, a costly single cycle penalty is incurred. And that's actually being optimistic. It would probably be a worse penalty in reality. So these graphs would actually have an even more glaring disparity between the simple and complex implementations. Therefore, counterintuitively, a more accurate second level branch predictor could often incur more penalties due to constant overriding penalties over this simple branch predictor that was very quick. And so this constant overriding is going to constantly eat into performance and constantly lower the instructions per cycle of these more complex implementations. This last figure here illustrates how, for a smaller hardware budget of approximately just 53 kilobytes, the results of the simple fast G-share implementation performs roughly the same, if not a little better, for most of the SpecInt 2000 benchmarks that were tested in this experiment. And it should be noted that with a much larger hardware budget for the predictors, the fast G-share implementation would likely far outperform the other more complex implementations with a more obvious disparity between the simple and complex implementations, as you could see in the previous graph on the right graph figure. But the point of this graph is not necessarily to show that the fast G-share implementation performs better than the others, however. It is mostly to show that it performs about the same as the other implementations, despite the fact that it is much, much simpler than the other implementations. So the added complexity really does not make that much difference in performance, even at a lower hardware budget of 53 kilobytes. And that is exactly what this graph shows. And that is like Jimenez's kind of like even this look points here in this graph. So we've finally arrived at a conclusion. The author concludes this paper by asserting that the large hardware budgets found in future processor generations will need to feature relatively simple branch predictor implementations with little overhead over complex predictors with more overhead. And this is confirmed by two ideas. The overhead of implementing a complex predictor can eliminate the performance advantage it might have had in the first place because of its improved accuracy. And the complex predictor organizations, they often unintentionally affect other aspects of the microarchitecture through unintentional dependencies, which involves techniques like overriding that bring a lot of penalties. And the simple fast G-share branch predictor of this experiment shows clearly that these problems of overhead and microarchitecture dependence can be overcome with implementations similar to it. Um, and the author then promised to continue to reorganize other branches, other branch predictor systems to account for the scalability of other branch predictor algorithms in the future. So he'd like to move beyond just G-share, and maybe he can manipulate, let's say, the multi-component hybrid system, if he can make that to not be so complex, to simplify it, to reorganize it such that it can also be more simple and thus not have all these penalties and be scalable with a large hardware budget, then the author would like to work on that too. And with all that said, that's all I have. Thank you for listening to this presentation, and I hope you learned all you could ever desire to learn about branch predictors today. If you have any feedback or are interested in this topic, please feel free to reach out to me here on Microsoft Teams. Thank you.